this course, we will explain some interesting ideas to build models that reproduce a physical or engineering reality with the purpose of solving particular problems. The central idea is to avoid the use of arbitrary hypotheses, which are often used to simplify and facilitate the mathematical treatment of problems. For example, supposing that a certain function is polynomial, trigonometric, parabolic, hyperbolic, etc., implies arbitrariness that possibly will not correspond to the conditions to the problem under study. Therefore, we try to analyze the problem to be solved and to discover the properties that it must satisfy. By imposing them mathematically, I mean these properties, we state differential, functional, or algebraic equations which will lead us to the only functions that are compatible with them. Therefore, we say that we use non-arbitrary hypotheses. In this way, the resulting model will reproduce the reality being analyzed, from which we can discover other derived properties as a consequence of this. We invite you to join us in this exciting task that almost certainly will surprise you. You will enjoy the new ideas proposed in this course, and we also hope this will suggest you other ideas that improve those here and to discover new models to solve the problems that arise every day in your field of specialty. During my long experience in refereeing papers, I have found many examples of incorrect models that become published in prestigious journals if nobody corrects them before publication and are used without any criticism. The consequences of using such models are unpredictable, because they can cause important errors and damages. A contribution to avoid this problem is one of the main motivations to publish this course. A second motivation is the idea of using the least possible number of arbitrary assumptions in modeling, and this is a new one. And finally, a third motivation is to extend the use of functional equations, a tool not inferior to differential equations that supplies relevant possibilities to solve this problem. In the course, I give you some examples. For example, the first one is the use of an inadequate formula. Some authors suggest to evaluate gas emissions by the formula E equal to C1 plus C2AV, where C1 and C2 are constants. E is the emission in grams per second, and A and V are acceleration and speed respectively. If you perform dimensional analysis, you find that the formula 1 has problems. First, it shows that C1 and C2 have dimensions, but they are not indicated, and then the formula cannot be used. The formula ignores relevant variables with the mass dimension, so that the authors need to include constants with dimensions. Then you can see that identification of valid and invalid formulas must be done with care. The second example is the use of an inadequate parametric family of distributions. To predict the 0.98 percentile of the temperature at a given location based on a sample, somebody can assume that temperatures are log normal. And then you take logarithm, we obtain the mean and the standard deviation, and then we use the formula for the percentile, and finally you recover the original population by using the inverse of the logarithmic function, which is the exponential one. The problem is that if a person in the United States uses Fahrenheit temperatures, the result is 105 degrees Fahrenheit, while a person in France obtains a percentile of 111.3 Fahrenheit, which is not only different from the previous one, but far from it. This occurs because the log normal family is not stable with respect to changes in location. That is, if the temperatures in Fahrenheit degrees are log normal, temperatures in Celsius cannot be normal. Thus, knowledge of what families of parametric distribution can and cannot be used has a high relevance in statistical modeling. The third example is the inadequate use of the domain of attraction for extremes. Consider an engineering design problem in which large winds play a decisive role. Then, it is extremely important to identify the distribution of largest winds. To this end, deciding among reverse Weibull, Gumbel, or Frechet is crucial. Thus, knowledge of the fact that finite or bounded variables cannot have a maximal domain of attraction of Frechet type is relevant. Selecting Frechet as the design distribution is an error and implies a very conservative position that can lead to unnecessary expenses. Thus, a good knowledge of what families of extreme value distributions can be used in a given case is relevant. The example 4 is a statistical incompatible model. Assume that we want to model the statistical behavior of a random variable xy, and we make the following assumptions. First, the conditional families of x conditional on y are normal. Similarly, the conditional families of y given x are normal too. And finally, that the variance of x given y is linear. In this case, no bivariate distribution satisfies these conditions. Thus, we are in front of an impossible model. Our assumptions are contradictory. So this justifies a general discussion about the conditions that can and cannot be imposed in order to have models compatible with the assumptions. The fifth example is the use of an incorrect extreme value probability paper. Suppose some people ignore that when dealing with extremes, there are two different probability papers, one for maxima, the right tail, and another for minima, the left tail, and that only tail data must be used. Using the inadequate paper can lead to serious errors and inconsistencies. For example, when predicting minimum temperatures, the use of the Gumbel probability paper plot in this figure reveals two errors. First, it is a maximal probability paper used for a minimum problem. And B, the model is fitted to all data when only the left tail data should be used. Contrary, this plot is the adequate one because it is a minimal reverse Gumbel probability paper, and in addition, the reverse Gumbel model has been fitted using only the smallest 40 data that is fitting only the left tail on the data. Look that the large data have not been used for fitting the model. All the above justifies the importance of clarifying the role of probability papers and the differences when they are used, A, to identify families of parametric distributions, or B, in extreme value analysis. The aims of this course are the following. We want to analyze some probability models used to reproduce random variables from the point of view of probability and dimensional consistency and physical validity. The main aims of the course are the following. First, to provide examples of random variables used in civil engineering models and to the corresponding families used to reproduce them. Second, to identify, analyze, and discuss the consistency of the most important models used in civil engineering. Third, to identify dimensional problems of some models and solve them by providing alternatives. Fourth, to clarify how an extreme value analysis has to be performed. Fifth, to discuss what type of multivariate random models are undetermined, overdetermined, or uniquely determined, and suggest ways to avoid the under and or over determination. And finally, to give rules to build models without the reported inconsistencies. In this course, we try to build models without arbitrary assumptions. That is a very important idea. Normally, mathematical models of real-life problems are built using convenient mathematical properties. However, when possible, we should avoid this approach. In this course, we base our models in properties that they are expected to satisfy. We start with the dimensional homogeneity conditions given by zoning. These are very important conditions that the reader should know. Zoning in 2001 indicates that dimensional homogeneity imposes the following constraints on any physical relation or equation. First, both sides of an equation must have the same dimension. We cannot add a length with a stress. That is a very important error. Second, wherever a sum of quantities appears in the right-hand side, all the terms in the sum must have the same dimensions. We cannot add a length with a stress, or a speed with an acceleration. We need to add a speed with speeds, acceleration with acceleration, stresses with stresses. And finally, all arguments of any exponential, logarithmic, trigonometric, or other special function that appear in the equation must be dimensionless. Given the dimension of a physical variable x, the dimension of x squared, of x to the third power, or even the square root, are known, and they are not the same as those of x. But what are the dimensions of log x, of exponential of x? What is the meaning of log meter, or log Pascal? That has no sense. Note, for example, that the exponential function can be developed in series as 1 plus x squared divided by 2. But look, 1 is dimensionless, has no dimensions. If x has dimensions, it cannot be added with 1. If x has dimensions, x squared has different dimensions than x, so you cannot add x plus x squared. It has no sense. So we need to be careful with that. One example of dimensional consistent model is the BPR model, which is the one given in this equation, where T0 and Ta are the length, A, free flow, and actual travel times of a highway, a segment of a highway. Eta and gamma are dimensionless parameters. Xa is the length flow, and Ca is the length capacity. It is dimensionally homogeneous because the dimension of the left and right-hand side coincide. They have time dimensions. Note the importance of using Ca in the equation in order to make dimensionless the ratio to be raised to the gamma power. However, the model Ta equal to T0 multiplied by 1 plus eta A xa to the gamma is not dimensionally homogeneous because the dimensions in the left and right-hand sides are different unless gamma is equal to 0. Even in the case of considering eta as a constant with dimensions, those of flow raised to the minus gamma power, its dimensions would depend on the value of gamma and would not be known before estimating the gamma value, which is a problem. And this is the end of my motivation to follow this course on model building. If you think that avoiding these errors is important and you want to learn the basic concept on model building, you are invited to follow this course, which by sure will benefit you.